My name is Chris Small. We're going to be doing the second webinar in the series, our first series ever. Hopefully, we'll continue to do that this upcoming every month for a while, but this is number 2. So let's go ahead and get started with economic benefits of high resistance grounding versus solid grounded systems. Like I mentioned before, my name is Chris Small. My wife actually tells me that I take pictures like Chandler Bing. So if you guys ever watch Friends, you would understand what that means. If not, then just know that I'm not the most photogenic person alive. So I'm a application engineer, regional sales manager for Post Glover Resistors. Been that way for about 12 years. Graduated with electrical engineering degree from Ohio State University. What year I will not say, but it's been a minute. So that's who I am, just so you know. And let's get into what we're going to be talking about today. We're going to be going into definitions, just to kind of set the stage, define what some terms are so everybody's on the same page. Now, keep in mind there's a lot of people on, there's a lot of people registered. About half of you are new registrants. You didn't see the last one. So we're gonna do a grounding overview, just so everybody's on the same page. I usually do that with most of my presentations that have to do with grounding because it's important. It's kind of a good foundation. So if you were here last time, you may, for the first 15 or so minutes, may have heard some of this before, maybe not, but it's a good way to get everybody on the same page. And then we'll go into the economic analysis between a high resistance ground and solid ground. That being said, let's talk about some definitions. Ground fault. Basically, you have a connection between a phase to ground that is unintentional. For example, if you have a wire running that was nicked on installation, it's running on a cable tray. It's the conductor is rubbing up against that metal tray, metal close enough with a little bit of air between, but metal on metal with a high enough voltage that it's going to arc. That's an example of assuming that cable tray is grounded, which it should be. It's going to be ground fault. So that's an example of that. Ground fault current path. Essentially, you're going to have an intentional ground fault. The ability for it to complete the circuit, but also go through ground to safely get rid of that current, so you don't have any electrified system. So there's usually a intentional ground fault system that's set up, and that is what that is. Ground fault protection is what we do. It's the detection of that unintentional ground fault, and either alarm or trip or etc. That's what that is. So moving forward, let's talk about system failures. This is an industrial study. We can look at a utility study, different studies. They're all very similar. The point is the vast majority of all your faults are phase to ground. That's important because when we talk about resistance grounding, which is what we do all the time, we're talking about a neutral grounding resistor, which connects between the neutral and the ground. So that's what we're dealing with. So if you have a resistance ground system, we are impacting the phase to ground portion of that system. So that 98% is what we deal with. Indirectly, we also deal with phase to phase. We're much less likely to degrade on a resistance ground system from a single line of ground fault into a phase to phase. So that's much more likely in a solid ground system. But it's a very small percentage. And then three-phase faults, usually somebody made a boo-boo. You have a serious issue, serious problem. Either somebody dug into a conductor, or who knows? Lots of different things can happen, but it's usually a man-made issue. That's a big problem, but also a very, very small percentage chance of that happening. So let's talk about. So I'm gonna do a comparative analysis. I do this because resistance grounding is, I would say, kind of in the middle, or maybe even call it a hybrid of an ungrounded system, and a solidly grounded system. So it basically tries to take the best of both of those situations. So if you know the issues with those systems and you know the benefits of those systems, you have a better understanding of why you want to use resistance grounding. So let's start with ungrounded systems. As you can see here, we have a ground fault on phase A. We have your three-phase, three-wire system here. Ground fault on phase A. It's not intentionally grounded. So how does it complete the circuit? So if you're looking to carry current or have any conductive current carrying path, you're going to need to complete the circuit. So the only path it actually has is through what we call the system's capacitance. Okay, that is an inherent to any system. It's inherent to any system. Basically, a capacitor is two conductors with an insulator in between. So we're talking about a lot of different things. We're talking about parallel cables, motor windings, almost everything in your system has a very small level of capacitance. And so it adds up to the system's capacitance. So that is a naturally occurring ground fault path. I call it leakage current, whatever you want to call it. The capacitive charging current is associated with that. And that's where you get the completion of the circuit. So in an ungrounded system, we have the issue with overvoltages. Why is that? Because if you have an intermittent ground fault, think of it as a switch, like you're closing an arc. Every time you close that arc, you're closing that switch and you're building charge. Well, there's no other path, as you see here, there's no other path besides through here to discharge. So you're essentially building up charge and building up charge. And IEEE talks about how you can get 6 to 8 times your rated voltage with that type of event on an ungrounded system. It's not a good situation. At that point, you're severely overvoltage, you're stressing your entire system, and you're probably gonna have multiple points of failure at some point, and you're gonna go line to ground to line very easily, and you're gonna trip with a line-to-line fault, probably some damage, obviously your entire system shut down, etc. Not desirable. One of the main reasons why you don't see ungrounded systems being specified anymore. There's a couple things as well, but that's the main one in my opinion. So we think about ungrounded systems, we think about overvoltage problems. Solidly grounded systems is I would call it from an historical perspective, the answer to that. You see ungrounded systems becoming or being popular in a lot of manufacturing in the 30s and 40s. And then in the 50s, you start to see, probably because of these issues, surging of solidly grounded systems. So solidly grounded systems is the exact opposite idea, right? So you were looking at a similar picture here, right? We have a three-phase system, although except for this three-phase three-wire system, now we have a three-phase four-wire system. So we can say a delta versus a Y. This is a Y. And so we have a bare copper wire, usually almost always very low impedance. And so the idea is you still have this naturally occurring system's capacitance that's carrying current, although typically small because it is usually a high impedance system. Because you're going to have insulation, potentially you're going to have air, lots of things that are high insulation that's going to prevent a lot of capacitance and a lot of current carrying capability in this path right here. So think about the same scenario I told you before. We have a intermittent fault or restriking, or that fault just keeps going on and off. We're charging that system. At this point, that's true. We are charging right here. However, over here we have essentially a discharge path. So this is a much more low impedance path. We're discharging much faster than we are charging. Therefore, overvoltage goes away in this scenario. So a solid ground system solves the overvoltage situation. The problem is because of the way it's designed. So the main idea of solidly grounded systems is you have very low impedance path, high levels of ground fault current potential purposefully. So you can easily see and very quickly eliminate the faults. So your exposure to personnel and to equipment is very small. That's good in some ways. In some ways, it's not good because especially with larger systems, you have so much energy that sometimes you can't clear the fault fast enough without damage, without life-threatening potential events like arc flash, arc blast, etc. So that's the downside. The overcurrents essentially are the downside of solid ground systems. As we can see here, IEEE talks about in their red book, basically you have a safety hazard exist. So what we're talking about here is typically an arc can create itself, an arc fault can create itself in about 2 to 3 cycles. That's typically not fast enough, or too fast, really, I should say. Your relay system, your ability to shut down is typically not that fast. I mean, potentially you could spend a lot of money, get some photo sensors, some pressure sensors, and do very high speed disconnecting, etc. And then people can do that. It's a high cost and high maintenance, but it's possible. But typically, almost all systems don't have that capability. And so therefore, arc flash is a big issue. So you can see here that the red book would agree with that. So just a quick review, or I guess a takeaway, I should say. All I need you to remember is overvoltages on the ungrounded system and overcurrents, arc flash, arc blast, etc. on the solidly grounded system. So we go to the resistance ground system, or we're specifically today we're going to talk about high resistance ground. And essentially we have the same. So I didn't put the exact same picture on here. Oops, I'll stay on this one. But think of it the same exact system. The only thing you're really changing is you're inserting a resistor in series between the neutral and ground. So what that does is a few things. Number one, you're maintaining your solid ground connection, assuming that the impedance of the resistor is less than that of the charge current, the capacitance, or maybe an easier way to say that is assuming that the current that's being carried or that's being allowed to go through the resistor is greater than the current that's going through the system's capacitance, then you have that discharge occurring and you don't have to worry about these overvoltage situations. At the same time, you have a steady voltage, typically, let's say it's a low voltage system, 240 volt line to line, 277 line to neutral. You have a steady voltage. You can use Ohm's law. It's one of the first things that you learn as an electrical engineer, and one of the easiest things. So basically, volts equals current times resistance, or another way to say that is current is inversely proportional to resistance. And so, assuming a steady voltage. And so, we have a scenario where we're engineering the ground fault current. I have a steady voltage. I can make a resistor anything I want, right? You can ask us to, make a resistor at whatever ohms you'd like, essentially. And so you can engineer your ground fault current. So therefore, you're eliminating the overvoltage, like I mentioned, and you're also eliminating the overcurrent issues that you have in a solid ground system. So that's what I was just trying to say before. So a couple of good things come out of this. Number one, it allows you to continue to operate. So IEEE talks about how at 10 amps or below, you can safely operate continuously with a fault. So that's high resistance ground is defined that way. That's what it is, 0 to 10 amps electric current. So it allows you to continue to operate. So this has been used for the last almost 50 years in a lot of process industries, especially oil and gas, but most process industries are familiar with resistance grounding, high resistance grounding, because of their continuous operation. One thing that I will mention though is that the last 10 or 15 years, especially, I'm sure some people have thought about it earlier than that, but it has become very popular to use high resistance ground based on the arc flash mitigation that it entails. Essentially, for all those ground faults you get, which is about 98% of the time, because of the amount of energy that's going through your system, you typically have 5 amps flowing through here to HRG, and you don't have a very high voltage, 277 volts, so you have a very low amount of energy. You also have voltage drop across the resistor, and so you essentially you cannot create an arc on a ground fault, on a high resistance ground system. So low voltage, high resistance ground system, ground fault, 0% chance of an arc fault, which means no arc flash, etc. So that's a big deal. It also can decrease shot potential due to stray ground faults, ground fault currents. So these are some positives of high resistance ground. And so whereas before, I would say 20 years ago, maybe more than that, but you know, everybody was talking about high resistance ground when their process was very important and they were losing money because they couldn't shut down their process without losing lots of money. So they would use high resistance ground. That was everybody's goal. Nowadays, you see a lot of people using high resistance ground because of arc flash mitigation. I will mention one more thing. If you're thinking to yourself, well, how does that impact an arc flash study? I will say this: it does not. Arc flash studies are worst case. Arc flash studies, just in case some people don't know, they basically dictate what kind of PPE gear you use, what kind of system you have, arc flash category, basically your procedures, etc. There's different categories, and you have to follow certain procedures based on your category. So it's just a safety protocol, essentially. So arc flash studies are designed to try to define that level, and it takes worst case scenario, which is not resistance grounding, so it does not impact that. But if you have a 95% reduction of faults, or excuse me, reduction of arc flash events, you can easily see that it's very important, regardless if it doesn't take away worst case scenario. So in terms of what IEEE talks about, I know just kind of give this as a reference. I'm going to go through some of these just to mention them. But I already mentioned a lot of the equipment protection and the shock hazards and getting rid of arc flash and arc blast hazards. Just a lot of good things it has to say, to be honest, about high resistance grounding. No arc flash hazard in the middle there. I probably should put from ground faults. It actually says no arc flash hazard, but in context in the red book, it is talking about ground faults. But you get the idea. So there's a lot of safety concerns alleviated, just to a certain degree. Once again, you're not getting rid of your phase-to-phase issues, your three-phase issues. So don't get me wrong in the sense that we're not eliminating the requirement for PPE. We're not getting rid of all your arc flash. I wish we would, because then not only would the world be a lot safer place, but also we would be on an island somewhere on the beach, because we'd be retired, because everybody in the world would be using high resistance ground. And they ought to, in my opinion, obviously, maybe I'm biased, but they should be. It's a lot more safe. That being said, if you like continuity of service, if you like arc flash protection, if you like those things, equipment protection, I don't think anybody doesn't like those things. You still need to know about a few things regarding how to design or how to implement high resistance ground. One thing we need to talk about is elevated voltages. So when you get a line to ground fault and you continue to operate with that, your original orientation or voltage of your three phases, individual line to ground, was 277. One of your phases is faulted, so therefore the voltage is 0 on that phase. The other phases, you were talking about an elevated voltage to 480. So we have elevated voltages on your two non-faulted phases. You need to worry about that. At low voltage, I'm not saying it's not an issue. It's not an issue with cable. It's already, and a lot of times it's not an issue, because a lot of your equipment is rated already for that. However, it's something you need to check. It's a good practice to specify high resistance ground and tell your providers that, look, we're using that system, and they may give you the same exact thing, or they may give you a slightly more insulated piece of equipment. Depends on what they do. So low voltage, this is probably, it depends if there's going to be any impact. At medium voltage, there's definitely going to be an impact. It's going to be you're going to be changing out wiring to more insulated wiring, et cetera. So it's something to consider. Loss of ground. Essentially, all I want to talk about this is you have a resistor that is typically alarming, and there's no tripping. Some people put their it's not required to have a ground fault breaker and to actually trip on any situation in high resistance ground system, since it'll never go higher than 5 amps. Some engineers like to have it anyway and just set it up for a potential short on the resistor or something like that, which it's fine. That's something you can do, but essentially you don't need to, and you're just alarming. But the problem is that if you happen to open up the resistor, then you can have an issue with a non-grounded system. And so you want to make sure you know that. So they have to have some kind of indication. So it's just important to know the loss of ground. Now I will say really quickly, I've never seen a resistor open up outside of shipping damage. If somebody drop kicks it off a truck, that's possible. However, in installation, loose wire, XO wire, a missed cable, etc., you're not going to worry about. You're basically going to have the loss of ground. You're going to know about the loss of ground because you have the alarm system. So you want to have some kind of indication there. Line of neutral loads essentially is the most important one in my opinion. So you have basically create a situation where your lines to neutral load has bypassed, essentially created a bypass to the resistor. A resistor is, oh, you know what? One thing I forgot to mention. I don't think I mentioned this at the beginning. I apologize. We're going to do a question and answer at the end. If you go ahead into the questions, you should be able to look at the question section. And if you have questions, go ahead and type them in. We'll do kind of a dialogue towards the end. Not just me and one of my colleagues will read the questions and we'll answer them, as many as we can. Getting back to this, you're essentially bypassing the purpose of a high resistance ground. The purpose of a high resistance ground is to be the sole, besides the inherent capacitive charging current, the sole path which forces the current to go through resistor and impedes the current that goes through. If you have a short through here, or maybe even a ground fault somewhere else, you are creating yourself an additional path that can bypass it, and so therefore you may have a fault. You may have a situation where you have a dangerous situation you don't even know. So it's an NEC requirement to not have this. Essentially, you want to use isolation transformers when you are. So what happens is you're going to isolate your line neutral loads. You're going to use an isolation transformer, solid ground those line neutral loads. Typically, this is lighting. Usually, if you look at a system, you have an existing system, you're going to potentially have 277 volt lighting. Usually, not much else. So if that's the case, you'd isolate that with the transformer, you solid ground that, and then you would and high resistance ground all the other important loads that you need to continue to operate. That's how you address that. So we'll start off with our first poll question. We're going to just give you guys a couple polls questions, simple questions, just to just to get some feedback. And we're not really going to stop. I don't think you really have time to get a snack, although I'm sure some of you will if you wanted to. But the point is that we're just going to do a quick break, which I'll end right now for the poll question. So we're going into, so we just talked about the overall comparative grounding analysis. And so hopefully you have a better idea of what each grounding method does and how high resistance ground works and why you may want to use it. But let's talk about, I would say, one I would say perception that a lot of end users, maybe even engineers, don't use resistance ground is because they think, oh, the cost is much higher. So therefore, we can't, the client has a tight budget, or there's, they don't want to spend extra money that they didn't think about. And that would be an additional cost, even though that we have all these other things that are great, which is not there. So that's what we're going to do. That's what today is for, essentially. We're going to go through the different parameters of a high resistance ground versus solid ground analysis, and then we're going to hopefully try to figure out how to do that with our own systems. So 3 categories to judge: installation, uptime, and incident costs. So let's talk about installation. So I just talked about isolation transformers. So we do have some adders for high resistance ground, one of which would be an isolation transformer potentially if you have line neutral loads. Once again, you may be able to get away with this. If you have a new system, you may be able to design it away. You don't have any line neutral loads. Maybe not, it just depends. But if you can't, you would use an isolation transformer. I wanted to kind of try to quantify that. I've already mentioned lighting is usually, if not the only load, the major portion of the load. So the Department of Energy talks about how for a manufacturing facility, you get about 10 kilowatt hours per square foot per year. And that's what a manufacturing facility would use. And so I kind of priced out a transformer that would cover approximately 13,000 square foot. So you might say, well, that's not very big. There's facilities that are hundreds of thousands of square feet. That's true. But a lot of times these facilities, yeah, you could use a larger transformer, but also a lot of times these facilities have multiple points of ground where they would have to use, if they wanted to use high resistance ground, they would. So you wouldn't actually have the entire building under one high resistance ground. Now, it's possible that you would, but a lot of times it's not that way. There are different processes that are protected separately, et cetera. So there is that. Cost adders for high resistance grounding. I know a little bit about this. So we're just going to kind of talk about, generally speaking, a budgetary price, about $10,000. Now, some of you may have experience and say, well, you can buy a resistor and an ammeter, and you can probably do that for a couple $1,000s. I mean, that's probably true, but there's a lot of things that you would be missing, and a lot of safety issues that you'd be having. And that's not really for today, unfortunately. But my point is that yes, there's a range, but I would say that for a manufacturer, $10,000 is a pretty good estimate of what you would use, and I would say that would get you a fully functional pulsing unit with a lot of features. I think that's true across the board for the most part. There are different manufacturers, but only a few. But the point is that that's a good budgetary price. It doesn't mean that's our price. It's a budgetary price for an overall HRG. Now, some other people might say, well, I paid $15,000. I paid $30,000 for a high resistance ground system. That is very possible. Usually that's a switchgear, HRG and a switchgear. So, I mean, I'm sorry if that's the case, but yes, usually you can get a standalone high resistance ground system for roughly a budgetary price about $10,000. If you need seismic, or if you need stainless steels or popular adders, just to kind of give you guys an idea of what the cost would be just on a budgetary basis. So on the other side of this, let's talk about what you maybe do not need on a high resistance grounding system. The NEC talks about how you do not need a ground fault main breaker on a high resistance ground system. These are typically larger systems. You don't necessarily have to. If you have a small system, the NEC does not necessarily require you to have that, but on some larger systems, they definitely do require that. So it's not required on a high resistance ground system. If you look at in switchgear, the size impact and the cost impact due to the size and obviously the equipment, usually we're talking roughly $5,000. Some of you may have an experience of a little bit less than that, but that's a typical price in switchgear. So if you're doing everything yourself, I'm sure you could save some money on that one. If you are buying it through in the switchgear sections, you're going to be looking at around that. So I mentioned before that you only need to have a single path to ground on a resistance grounding system. You do not need a neutral anywhere else. You obviously need to go from XO to the resistor to ground. You shouldn't need to carry the neutral anywhere else, which means that you'll have a neutral wire slash bus that you don't need. So essentially, there's cost savings there. We estimated this to be around $2,700. Also, if you basically put the HRG next to the transformer, you're going to be saving a lot of money there. And actually, you don't have to put it next to the transformer. But the point is that on a solid ground system, you need to carry the full capability of an ungrounded phase conductor, I should say, phase conductor on your neutral. So therefore, whatever your system can handle, you need that wire. So on a 1,000 amp system, which is not that atypical for a industrial application, we're talking two large cables that have to. So however far away your system is, if you have to run it to your switchgear, you're going to be saving yourself some money because HRG requires you to only have 8 gauge. That's an AC requirement. It's the ampacity, which is typically 5 amps for a high resistance ground or somewhere in that range, with a minimum of 8 gauge. So you're basically using 8 gauge. So it's much less on the cost side. So you're saving a lot of money on that as well. So now, there are more things than this, and we'll talk about a couple in a second, but your basic idea of what you need for solid ground versus a high resistance ground system, the perception of, oh, this is going to cost me a lot of extra money, I don't think is necessarily a good perception. Now, that being said, there's always situations where it's very possible that installation on a high resistance ground system is more than a solid ground system. There are a lot of variables, and we'll go through, I guess, the majority of the ones that we haven't talked about in a second. But the point is that I don't want you to think that HRG is always going to be less expensive on installation. But however, I want you to open up yourself to the possibility and also the likelihood that it could be. And so the stuff we haven't really talked about, it is important. I did mention before that how do you deal with line to ground voltages elevated? Now, on low voltage systems, once again, I'll kind of repeat myself a little bit. It just depends. If you have a lot of, if you have a lot of UPS, or if you have a lot of drives, et cetera, that are not made that way to handle elevated voltages, there could be a cost impact. There's just so many variables that's hard to quantify. I will tell you this though, that on low voltage, it's much less likely than at medium voltage. You have a large impact at medium voltage. So this conversation is kind of geared towards low voltage. But if you've used medium voltage high resistance ground before, essentially you need, let's just give a quick example. You have a 5 kV system. You want to continuously operate a high resistance ground system. You essentially need a kV cable. So that bump up in cable throughout your system could be a significant cost increase. So I'm just trying to differentiate. Also, I wanted to mention this because some people don't understand this. A lot of times you want, in an industrial setting, you want to use a delta Y transformer, some isolation there. There's issues with the Y to Y transfer. Sometimes you don't have a choice. Sometimes the utility says, you have to use a YY transformer. I just wanted to mention it because there is a cost differential. Sometimes the utility would get, if they own it or if you're going to buy it, depends. But they're going to a lot of times give you a cheaper Y to Y transformer, which because essentially it's cheaper because of the less insulation. Now I will say that I don't recommend using a high resistance ground on a Y-to-Y transformer. Theoretically, it is possible, but typically the reason why it's used, in my opinion, is that you're reducing cost, reducing insulation. If that's the case, if that's what's happening, you cannot use a Y-to-Y transformer on a high resistance ground system. The high resistance ground system would require a Y-to-Y transformer with elevated insulation, and typically they're not made that way. So just want to kind of throw that one out there. These are things that we didn't really talk about, but things to think about when you're doing an analysis. The second topic is uptime. So in terms of the differential between solid ground and high resistance ground, solid ground is going to trip, right? That's obviously how it's designed. We've already talked about that. A lot of times you have an instantaneous trip because of the large amount of current on a solid ground. You could coordinate it properly and never trip your main, but you are taking time to do that, and therefore you're allowing more damage. So there's a kind of a damage versus coordination trade-off that you need to wrestle with on a solid ground system. And so I've had many situations where I get a phone call where an operator, a facility, they have just completely shut down their main, and their entire facility shut down because of a ground fault. And at that point, they typically get some kind of a resistance grounding system because they understand the impacts. But the point is that there's a huge difference, right? Uptime versus downtime. So if you have ground fault on a solid ground system, you get downtime. On a high resistance ground system, you don't. So just a quick differentiator there. In terms of downtime and what that costs different data centers, industries, I'll give you an idea. Data centers are one of the larger ones. They typically, to be honest, their average downtime costs is much less per event, but usually they're down for a very short period of time, and like we're talking seconds or maybe even a very short period of time. But the point is that their cost per minute per hour is huge. They have a lot of people that are depending on them for uptime, and that's the essence of their business. So there's that. 531K per hour. That's a lot. Oil and gas. They did a study about the average refinery loses $42 million a year. Now to go into that a little bit further, just a little bit, about 60% of that typically is planned downtime. So you don't have it quite that much in terms of what high resistance ground could help you, but that 40% of unplanned downtime is a killer. So that's actually, it costs a lot more per event. You do have planned downtime, obviously, for maintenance, et cetera, but the unplanned downtime is what gets you in terms of money per event. Just some different industries, just to give you a flavor. Aberdeen did a study a couple years ago. They talk about how the average, they did, I think it was, I want to say 490 it's roughly the number. Probably should throw on there, but it's right around there in the 400s. They did a survey of all these different types of businesses, which include all kinds of people. And they came out with that the average is 260K per hour. So that's a lot of money for downtime. So just to continue that real quick, in terms of data centers, I wanted to say that, look, this is not always good. A high resistance ground can't help with all of this downtime. You have hacking, you have a lot of different reasons, software failure, even some hardware failure that's not power related. There's things that can happen that high resistance ground can't do anything about. But the point is that a large percentage of that it can, and that's what that 25% is essentially. UPS failure. If you have a high resistance ground system, once again, you can operate with the fault. So instead of switching over, or maybe you do switch over on your double-ended switch gear, but then you get another fault, and then where are you going to go? You can shut down, or you can just run on a high resistance grounded faulted system, and you can continue to operate there. So that's helping the issue. You get rid of that. If the UPS fails, you're going to be able to continue to operate on that power. So a similar study was done by G. Vanson Warren. 450 company survey included manufacturing, medical, oil, gas, energy, and transportation. So on average, there was about 2 outages over 3 years. And per outage, the duration was 4 hours. So some people had 0, some people had much more than 2, but the average over a 3-year period was 2 outages. And roughly 45% of that was due to equipment failure. So that's kind of part of the pie that we're looking at. The point is that I don't think people look at how expensive, especially nowadays, it's increasing. It's not quite exponential, but it's increasing significantly every year. I think it was 40% increase in a couple of years in terms of downtime for these industries. So we're talking about a large percentage of money, which higher resistance ground can definitely help with. So let me give you just a small business example now. Small manufacturers, this is made up, but I just want to give you an idea of how you would calculate this, just for basically production loss. There's many different ways you can lose money, opportunity costs, etc. But so basically, just the production loss. You have a $50 million revenue company. Typically, we're talking about, a small company about roughly 100 employees. One shift, typically 2,000 production hours would be one shift, and then you have, take that average that we showed in the last slide, and you have 8 hours overall of downtime, and that's going to cost you about $200,000. So you get the idea. These things add up. Downtime is a big issue. Once again, will higher resistance ground help with 100% of this? No, but it will help with a lot of it. And I can't quantify it, but I've tried to a little bit in the data center world. Obviously, I did a little bit, but the point is that loss due to ground faults, lost time due to ground faults is definitely an issue, and higher resistance ground will help with that. Poll question number 2. Essentially, just go ahead, fill it out. We'll get the results back to you right away, and we'll go through to the last section of our webinar today. So incident cost, there's a 7-year analysis on fault losses. The average cost of the company was about $750,000 per fault. So we're talking about, typically, I can't say for sure, but typically we're talking about solid ground systems where you have a ground fault, which almost, once again, 95% of the time, it starts out that way. And you can get a situation because of all the energy to degrade into a phase-to-phase or even potentially a 3-phase fault. And so that's where typically you have your damage. So average cost of company, it's a lot of money per fault. So I go to a reference book to kind of dig this up. Essentially, if you look at high resistance ground versus solid ground, we're talking about a very low current for a longer period of time, or a very high current for a short period of time. So if you're talking about that, you would think that, well, maybe they're kind of almost the same, which is intuitively correct, but not true. So, but the problem with solid ground systems is you can experience thousands of amps, or maybe even 10,000 amps on a ground fault current. That's a problem, because even if you have a very short time window where you have exposed your equipment and potentially your personnel to that, it's probably not going to be small enough to that where you don't have damage. So on the other hand, on the other side of that, you have, let's say, a 5 amp resistor, high resistance ground, but you're continuously operating with a fault, so your time is much higher. So you think, well, okay, if I multiply that, it's going to be, probably going to be a little less, but still going to be kind of high. But the point is this: IEEE talks about how at 10 amps or less, you can go as long as you'd like. You're not going to damage your equipment. So that's not exactly true in terms of my first statement, although it's a good rule of thumb overall. But for 10 amps or less, we're basically talking about 0 additional damage. If you have a ground fault, something's happening, right? But you're not going to be stressing the remainder and hurting the rest of your system. So obviously we talk about how can we get rid. So if the overall damage is in terms of fault current time, then if we can reduce both of those, then we can get stuff like preventing burn downs, reducing repair costs. This is all in this reference right here. Reduction of maintenance of breakers, and talking about generators, transformers, motors, and talking about repair versus replacement. There's a lot of variables in this, and I'm already gone long, so you can kind of see I had to kind of pick my battles in terms of how detailed I wanted to get about each of these categories. But I guess the main goal to do a white paper and to get into heavy details about potential costs, all this stuff is a possibility. But the point is, for this venue, I want to give you guys the tools to know what to look for and to think about when you're comparing the costs of a resistance ground versus a solid ground system. So we're talking about on an incident cost, we're gonna have reduced cost on a high resistance ground system. You're gonna have less additional damage on a high resistance ground system as you would in a solid ground system. That's the point. So once again, our resistance ground will drastically reduce the ground fault current. I've been through some of this already. Five times less likely to grade to phase in a solid ground system. This is kind of review, so we'll kind of go fast through this. It eliminates 100% of arc faults on phase to ground faults. 98% of your faults, you can't have an arc fault. It's a big deal. I've talked to, so I do a lot, I used to do, I should say, a lot of startups, a lot of maintenance, a lot of troubleshooting in the field. And to be honest, about 50-50 response on high resistance ground. 50 people were kind of wary of it, but that 50% was completely in the dark. They needed training, and that's what I was there for. So after the training, they were much more comfortable, and they understood how much safer they were, and so that they felt good about it. And the other 50% already was kind of there in the first place. So there's not a lot of maintenance personnel who understands high resistance ground. It's not going to like it. They may not like the alarms, but if they understand how much safer it makes them, they'll definitely go with that for sure. There was a study done on a potential savings of insurance for using a high resistance ground system. I will say this, I definitely something I would explore if I was an engineer and or an end user looking to use these systems. I would explore that my insurance company and see if that is offered. I can't say that all insurance companies are aware of this idea, but the few that are, actually, to be honest with you, I don't know for sure how many at this point are. This was done a few years ago in terms of this article, but it's a safer system. So it makes sense to get potential savings off of your insurance. I would definitely, if you're an engineer, I would definitely use that as a potential selling point for a high resistance ground system over. If you're talking about premiums, 10% saving, that's a lot of money. So in conclusion, I don't want to go, I know I painted the picture, and I'm not, it's definitely not wrong, but I don't want to be conclusive about what's cheaper, or which one, high resistance ground or solid ground system. I could do a case study, and all day long I could show you instances where high resistance grounding is cheaper. You could probably do the same thing opposite. You could pick and choose your installation. Obviously, that's not the point. None of us pick and choose our installation. Essentially, we have an application, and we try to solve it. And so having these tools and figuring out how to calculate what my costs are can help you. So that's more the point. But you can go either way. And I'd say it's very likely that a high resistance ground will save you money. It also ensures more uptime. There's no question about that. A lot of times you can spend several hours trying to get up again on a solid ground system. You're not going to have that on a high resistance ground system. You're either going to shut down a certain section of your system and fix it, or you're going to basically deal with it at a later date, typically at the end of a shift or the end of the weekend. 95% arc fly mitigation, obviously it's good. And then it's just I think it's, if you have the personnel to use high resistance ground, I can't think of a reason why not to in industrial, larger, heavy commercial or industrial applications. So that is what I have for today. I think at this point we are going to be going to question and answer session. Thank you guys for your time. Hopefully you'll stick around. But let's go ahead and open it up to some questions. Stu, I think you're gonna. No, you should be able to hear it through this.
Okay. One of the questions, and there were quite a few questions. Thank you all very much for posing them, and I guess I'll say paying close enough attention to know what to ask. One of the questions from earlier in the presentation was, does NFPA and/or IEEE 1584 allow consideration of the reduced ground fault current in the hazard determination? He said he's aware that the calculation is based on three-phase fault current, but does it not take into account the fact that if you limit to 5 amps, you have less potential for a hazard?
Not at the moment. I think I hopefully made that clear. Maybe I didn't. Hopefully that question was before I kind of explained it, but essentially no. At the moment, no, it doesn't. There is no impact. So you are correct. But I do know of a potential to put probability in the equation. Now I'm not creating news here. It could be, sometimes these things take years and maybe even longer to actually get implemented, but that is being discussed currently. And so I can hope that makes it in there, but as of right now, that is not the case. So like I mentioned before, resistance grounding, high resistance grounding has no impact on arc flash studies.
I'm going to combine two questions. One is, when you use HRG, where in the system is the HRG located? Meaning, what is the connection point? And the other one is, what is the maximum distance HRG should be installed from the transformer?
Okay, so for the second one, essentially you have a situation where, well, I guess they're both the same, like you said. So the ideal is you're going to have it right next to the source. So you're going to have a generator or a transformer XO right to the HRG right next to it. Does that mean you have to have it that way? No. It's very popular to have it in switch gear, but typically a rule of thumb is to have it as close to the source as possible. In terms of how far can it be away, well, you have to think about a couple things. Number one, just in terms of the resistance itself, usually it's going to be a decent amount of distance before it impacts. So for example, you're adding resistance, right? When you have, let's say you have an extra 1,000 feet of wire, just to be a little bit extreme. Maybe that's not extreme at all. I'm not sure, depending on where your point of reference is. But the point is that you're adding resistance in your wire. So therefore, your resistance is changed from that resistor to the resistor plus 1,000 feet of wire. So you need to take that in consideration. So usually, good rule of thumb is to keep it as close as possible. You also have to think about communication stuff as well. Depending if you use contactors or if you use, depends on how you're communicating. Obviously, if you're digital, it doesn't really matter. But the point is that there's a few different considerations on how far away you want to go. But basically, you want to have it as close as you can. But I think you understand that you're impacting the resistance based on the distance, so you can figure that out.
Another question, for a main tie main setup, how many HRGs should be used, 1 or 2? And if you use 2, how do you manage when the tie is closed?
Yes, typically 2 is the correct answer. I can't think of a good reason why you would use 1. If your tie is closed, you're essentially paralleling your resistors, which is not the end of the world. Instead of 5 amps, you're going to be.
Unless you're not using sources.
Oh, that's true. That's true. Stu reminded me that you may, if you're just using one source, you would just go through, because there's no connection back to the source because there's only one being used. you would just use the one resistor. But the worst case scenario is you would be using two if you're paralleling your sources. So that's the consequence, not a not a deal breaker, but typically you would not use it that way. But maybe I'm not. Maybe the person who's asking the question has a scenario like that. But basically you're paralleling them, so you're adding your ground fault's additive. So in this scenario, it would be 10 amps ground fault current, which would still be fine to operate continuously.
Delta Y transformers on high voltage transmission systems typically are solid grounded. Why wouldn't they use HRG at high voltage?
Well, so one of the things about resistors, well, okay, so there's a couple things actually. Number one, actually, let's go through the most important ones first. The amount of energy you can create, let's say you operate, let's say let's just be a high example, let's say 35 kV. You're 35 kV, let's say you have 10 amps HRG. Think about how much energy you're continuously operating with. At that point, arc flash is no longer, so when I'm talking about arc flash mitigation, hopefully you guys, I may have not mentioned this, so I apologize if I didn't. But I'm talking about low voltage when I'm talking about all this arc flash mitigation. So if you have that much energy in your system and you're running continuously, that's just too much energy. We're talking arc flash everywhere, problematic. So the other reason, and this is kind of it doesn't even matter because the first one's important, already killed it. But the second one is it becomes extremely expensive to do it at high voltages like that. So typically, if you're talking about high resistance ground, by high resistance ground I mean system, pulsing system with alarm only, and we're talking about typically 5 kV or below. And for generator protection, usually we're talking 15 kV or below. Anything above that is not practical and also not safe.
I'm going to hijack a question that was asked by a longtime listener, first-time caller, Bill. He's asking what type of HRG is recommended on a 40-volt wall-mounted power panel fed by a specific transformer. What I'm going to rephrase to Bill, if you'll permit me, is the HRG size based on the transformer that's feeding that system?
So the answer is no. The HRG, essentially, there's two things to consider that I can think of. Hopefully, I'm not missing anything. I'm pretty sure I'm not. So the voltage is obviously important because once again, Ohm's law, volts equals V equals IR. So if you change your volts, you're going to change your resistance, or you're going to change your current based on the resistance. So it's very important to know your voltage, right? The other thing that's important to know. Oh, you obviously want to. Well, if you want to know your capacitive charging current, just in low voltage, I want to be careful. In low voltage systems, I don't necessarily recommend doing analysis. I think it's not necessary. It's, historically speaking, or customary wise, you basically have a situation where engineers never have done charge current analysis. They've done a 5 amp resistor, and they've never typically had issues. Rarely would they have issues with capacitive charging current. On a low voltage system, you're not having issues with that. Medium voltage is a different story. You're going to have to do some kind of analysis, some kind of calculation, and see if you could even use it, because at that point you may not be able to use high resistance ground because the charge current would be too high. And if, just as a review, if the capacitive charging current is higher than the resistance current, then you're going, or the resistance let through current, then you're going to have overvoltage issues potentially. So I guess short of it is no, it doesn't matter. It's just the voltage and the capacitive charging current.
Typically, when a resistor fails, does it fail open or closed?
I don't know the answer to that. I mean, usually, I would say actually I do. I mean, usually it's open, but I mean, I've seen on these types of applications. Now, there's different resistors for different applications. If we're talking load banks, if we're talking different things where you have a lot of use, a lot of power for a long duration, yes, I mean, there's failures there. But on high resistance ground systems, once again, I'll go back to what I said before. If it's been delivered safely and not without damage, somebody didn't kick it off a truck. Very rarely. I can't think of a single example of a resistor failing. I've seen neutral wires get dug up. I've seen open neutral wiring that wasn't installed properly. But I've never seen, I mean, I've even seen people physically break the resistors because they accidentally lean on one. But the point is that, yes, they're going to open up, but I've never seen it. That being said, that's not a good enough engineering reason to not have neutral monitoring. So you should have neutral monitoring just in case it can happen. Just to give you an example, it's just that I thought in my head, even though I haven't seen it in the field. Basically, you have a partially damaged HRG that happened via transit. You don't actually notice it is made microfractures. You still get your at this point your ohm readings are still good, at least good enough, within 10%. But after years of potential ground faults, I guess it is possible for that damage to increase. So you might you're probably gonna have a different, you're gonna start seeing different currents before you're gonna start seeing actually open resistor. But the point is that it's very rare. I don't know of a single situation that's happened. So, but the bigger, just not to go on too long, but the bigger point is it can happen where you have installations where somebody makes a mistake. I've been at several of these installations. My colleagues have been at several of these installations where it's already started up. It's been running for a month or two. They're having issues. They're having these alarms. Why is my system alarming? They forgot to, they put the XO wire into a terminal strip, and there's the HRG neutral is 3 feet away, but they forgot to connect that wire, or they forgot to do the exact same thing on the transformer side in the transformer cabinet, or they just had a loose connection because they forgot to tighten down per regulations the way they should have. Those are things I've seen a lot. Now the other stuff not so much, but that's why you really want, in my opinion, what you really want open neutral monitoring system for that purpose, because you don't want to be ungrounded and not know it. That's a bad situation.
There are, on behalf of Chris, thank you all very much for both your attention and for all the questions. We will not be able to get to all of them today, as I realize people's schedules are quite busy. We will do our best to reach out to you and get you an answer, or at least point you in the right direction toward an answer, depending on the question. You may feel free to email Chris directly at the address he gave you, or send us an email at support@postclover.com, and we'll try and get back to you and get you the answers you need. One other question, Chris. Where do you install HRG in switchgear? So if you had to line up with switchgear and you want to incorporate an HRG unit, how do you do that?
I mean, typically it takes I don't know if where it actually matters, but you basically want to have it where you can easily tie to the XO and or maybe even the XO of the switchgear section. Typically the way it is installed is in a half section. The control panel is in a half section of switchgear. And then you have the resistor either on top of the switchgear section or potentially in the back. So in terms of location on the front, I don't think it matters. But once again, take into consideration you want to as close to the source as possible, and you want to keep the resistor away from the controls, both your switchgear and the HRG, because if you guys who do switchgear do temperature studies and figure out if you have a resistor that's continuously operating at 385 degrees C inside your switchgear, that may cause an issue. If it's in the back, like a lot of switchgear manufacturers do, then you're probably okay. If it's on top, then obviously you're okay. But so that's where I see HRGs installed in switchgear.
Possibly the last question. You brought up data centers. How does an HRG affect a UPS system or vice versa?
Okay. There are some things that you have to worry about with UPS. To be honest, I would say UPS is probably the most tedious piece of equipment to use with the HRG for a couple of different reasons. Number one, a lot of times the controls on the UPS needs to be solidly grounded in order to operate correctly. I shouldn't say a lot of times. A lot of UPS systems have it that way. So there's a problem. There's a conflict right there. That being said, this has been high resistance ground has been around for a while. There's a lot of UPS manufacturers who understand this issue, and so they typically create a UPS for high resistance ground. So you may need to have additional insulation based off of the elevated voltages I discussed. You may have to have a different way of controlling the UPS because you cannot effectively solid the ground, the system, and create an extra ground path. But usually those are workarounds. The other issue, potentially, although I haven't seen this very often at all, the charge current can be high in the UPS system. There's a couple things to point out. I mean, I've seen, especially very new systems. I'm dealing with something right now where there's a UPS system with about 8 amps of charge current. We're actually dealing with it with a 10 amp resistor. The rest of the charge current is very small. So we are actually still using a high resistance ground in that system, but especially with the very brand new stuff, you definitely want to keep count of the capacitive charge current. The last thing I could think of is that there's a lot of these UPS systems have a lot of backfeed, a lot of noise. Not to get too far in the weeds, we actually have a capacitive charging current measurement feature that can be impacted by all of this noise and backfeed. I'd typically recommend during startup, if you have a UPS system, to leave it in the system, but to disable it or turn it off. You should theoretically still be able to measure its capacitive contribution, but all that noise won't be impacting the measurement. So I guess those are all the things I have for that question. But yes, I mean, you need to worry about UPS, and so there's definitely consideration there. So you typically have to use a special, I don't want to call it special because it's used a lot. I mean, we sell thousands of HRGs in the data centers. So don't get me wrong, and they all use UPS, right? So, but at the same time, you need to make sure it's all working right and copacetic. So you need to take some care into figuring out how the system is designed so that it can work. They can both work properly together. Okay, I think we're done. So, guys, I'm sorry once again. There's a lot of questions left. We're going to get to you via email, but we're kind of going not long, but we would be going much longer if we try to answer all these questions. So we're going to leave the rest for email. Thank you guys for your time. Really appreciate it. Hopefully you'll be around for the next one. We'll have in about a month, and everybody stay safe out there. Appreciate your time. Take care.